Hello everybody. In this video, we will discuss mask RCNN. This is an example of instance segmentation and we'll read about it. So let's dive right in. Until now, we have covered image classification. Again, to remind you, in image classification, we have an image as an input and the output is a single label for the entire image. In semantic segmentation, we have an image as the input and the output is one label per pixel, right? So if there are two cats, they will all the pixels that belong to the two cats will have the same label. So it's very useful, if you want to do semantic, if there is like this kind of a Zoom call where you want to remove the background, you know that there is only one person and you want to remove that, you can use semantic segmentation for that. But if there are multiple people and you want to do counting kind of applications, then semantic segmentation is not useful. You may want to use something called object detection. In object detection, you can have multiple objects of different classes, and the input is an image and the output is a collection of bounding boxes that contain those objects, and you also have a class label for every bounding box, right? Now, all that is interesting, but what if you could do something, combine all the good qualities of semantic segmentation and object detection, which means that not only is every pixel labeled which class it is, we also know which instance of that class it is. So if there are two cats, we'll be able to tell that this is cat number 1 and this is cat number 2, and we'll have masks for both of them, not just bounding boxes, but we'll have masks for both of them. Okay, so that is called instance segmentation. It is basically combining the ideas of object detection and semantic segmentation. All right, so here is an example, right? We had this sheep and a dog, and you can see that if you do semantic segmentation, these sheep are overlapping, so it will create this mask. But it won't be able to tell you which pixels belong to sheep 1, which pixels belong to sheep 2, and which pixels belong to sheep 3. They are all just labeled as the sheep class, and we have the dog class. In object detection, we are able to identify them separately. You can see that there are separate colored bounding boxes, but we are unable to tell, which pixels are. Everything in the bounding box, we say, is in that class. So it's a coarser representation. Now, in instance segmentation, we basically marry the good ideas of these two methods, and you end up getting something like this, where you have a dog class and everything that is blue is a sheep, but you have 3 different sheeps, right? So you have 3 instances of the class sheep and 1 instance of the class dog, and that is why it is called instance segmentation. Here you can see is an example. There are multiple people. All these people, they belong to the person class, but they can be separately identified as, okay, this is person 1, person 2, person 3. And then we have the elephant class, what looks like an elephant class. So the best method currently available for instance segmentation is called mask RCNN. It is from the same group that created RCNN, fast RCNN, faster RCNN, and now mask RCNN, right? So they are, it's very interesting because they are building on the technology that they started, and they've been building with new ideas. And a lot of times these ideas are very clever, but not, they are very clever, but tiny ideas. They come up with something very interesting, and but it's not very difficult to understand. And that idea actually works to solve the next level of the problem, all right? So this is mask RCNN. I'm not going to go over the architecture of mask RCNN, but we'll go over how to use mask RCNN. So let's, by the way, the architecture, etc., the details of mask RCNN, these kinds of architectures, they are covered in our courses. Deep learning with Pytorch, for example, is our deep learning course. So if you're interested in a career in AI, you can take our programs, right? You can go to opencv.org/university, and there we have a bunch of paid programs. You get excellent support for it. You can try those out, right? But if you want to dip your toes in AI and just get a feel for what it feels like, this is the right course, right? This free course is for that reason. All right, so we start by importing some dependencies. We do the PIL library, matplotlib, all the standard libraries that we have gone over, several notebooks. I'm not going to go over them. We assign a random seed so that, you know, our experiments are reproducible. And then let's look at the syntax, right? So if you look at the output, the input is very clear, right? In case of you know, instance segmentation, the input is basically a color image or a collection of color images, and it's basically has to be in this format. You have to put in the channel first, then the height and the width, right? That's the input. The output is slightly different, right? In the output, we remember what are the various things we need in the output. First of all, we need a collection of boxes. We need the collection of bounding boxes. We need masks inside every box. We also need the label that corresponds to what label it is, right? What class it is. So sheep is a class, for example. And then we also need the confidence score so that we can do thresholding and we can select, you know, based on the confidence, whether or not we want to call it an object or not. So those are the various things that we need. And when you get the output, right, it is in this format. It is list, and then we have a dictionary, and then we have a tensor, right? And this dictionary has these fields. We have the boxes. This tensor is n by 4. N is the number of objects that have been detected. And the boxes are basically x0, y0, and x1, y0, y1. These are the 2 points, the top left corner and the bottom right corner of the bounding box that contains the object. Then we have a label. You know, we have a tensor of n elements, and these contain the labels like sheep or dog or something like that, right? Then we have the scores. The scores are basically between 0 and 1, and you can use threshold the scores to find only the most confident results. So scores is there. And then we have the mask, right? Again, the mask is, this is an image, and we have n different masks, and we have height and width as the channels, right? So the predicted mask for each instance is between 0 and 1, right? It gives you the confidence, right? How confident it is about pixel values. So even if in the sheep region, you will have all these pixels. So you can think about this tensor, this mask tensor, as an image with multiple channels, right? Just like we have an image with 3 channels, RGB, the mask is an image with multiple channels, right? N is the number of classes there are. And I think in this case, it is 21 or so. It is trained on. We'll find out. So for every class, we have you know, the scores, right? We have the masks. So if you want to find what, you know, for a particular pixel, if you want to find out what is the class for this pixel, you need to take a max of all the pixels, right? So along that pixel, you have to take the mask of all the channels, right? You have to take the max of all the channels, not the masks. So once you take the max, you will find which, for this particular pixel, which channel has the highest probability, right? And based on that, you will see the score. Okay, so let's go over this. The very first thing is we basically get the model. And this model is called mask RCNN underscore resnet 50 underscore FPN. And it's basically the same way we have done other models. We are going to load this model. We are going to provide the weights as the standard weights, the default weights. We are not going to train this model. And then, and then we set this model to eval, right? We are saying that this model will be set to evaluation mode. As we know that in evaluation mode, the model becomes faster because it drops some of the things that it doesn't need for training. So it is very important to set it to evaluation mode. Then we have Cocoa instance. In the last notebook, we mentioned what the Cocoa dataset is. So the number of classes is actually 80, not what I had mentioned earlier. It's not 21, but it is 80, right? So all these classes we can do instance segmentation on because it's trained on the Cocoa dataset. All right. So that's great. And then we want to assign a color to every class, right? When we create a bounding box, etc., we assign a color to every class, and that's what this line does. So the colors are randomly assigned and stored here so that we can keep using the same color over and over again. If there are multiple instances of the same class, we are going to draw the bounding box around it with the same color. Okay. So we have the very first utility function we have. It's called random color masks, and basically it takes an image and basically colors it it overlays a mask on top of it, which is a particular random color that we just chose. Okay, so here, for example, let's go over it. First, it creates 3 channels, R, G, and B, and the size of the channels is the same as the size of the image, and it fills it with zeros. Okay, and this image is also, it's basically uint 8 type. Then we assign a random color to it, right? Basically, this image that we had passed in, it is a mask, and this so it's basically 1 at places where the mask is white, and it is 0 at places where the mask is dark. So we are going to change this using, we are going to filter all the pixels that are 1, and we are going to assign to those pixels, we are going to assign a random color, right? And so basically, if you look at this, if you look at these people, there is a slight overlay on the person class, right? We have drawn a bounding box, which is the color pink, but you can also see that there is a slight overlay, and this person is a slightly different color. The overlay is slightly different color. This person, the overlay is slightly different color. So every one of these instances is colored slightly differently because it is randomly chosen. Okay, so that's what this masking does. It's basically overlays a thin mask on top of it, and we'll see how we blend it. Okay, so we get the random color mask. Next, we get prediction, and this code is going to look very similar to the one that we saw for faster RCNN. So we load the image, we convert it to a tensor, and as I had mentioned before, this code also doesn't require you to convert the image to a particular size, right? Internally, it is going to resize the shorter dimension to 800 pixels, and the longer dimension basically preserves whatever is the aspect ratio, and that happens internally. So you don't have to do any pre-processing. All you need to do is convert this image into a tensor, right? So that we can use it with Pytorch. Then we set this no grad. As you know that if you set Torch to specify that you don't have to create any, you don't have to worry about gradient calculation, the inference becomes very fast, right? So to do that, we are specifying torch.nograd so that no gradients are computed, and we make the prediction. To make the prediction, we just pass this image into this model, right? And once we do that, we get this object called pred. Now we are going to pick the first element of it, which contains all these things, right? The scores are there, and you can see here we are going to convert it to a NumPy array, and we have seen this again and again. The way to convert this thing to a NumPy array is to first detach it, so that all the computational graph, it is dropped from the computational graph. Then we move it to the CPU and then convert it to NumPy, right? So this is the standard method we have been using. So we get the scores. We get, as I had mentioned before, this object pred prediction data is a dictionary that contains these 4 elements. All right. So we get the scores out, we get the labels out, we get the bounding boxes out, and we get the masks out. And here we are, binarizing the mask. The mask that we get is actually not, it's not a binary mask, right? It is valued between 0 and 1. We are going to binarize the mask right here. Anything above 0.5, right? And then we get the masks. Now, we also want to make sure that the scores, we are only looking at bounding boxes where the scores are above a threshold, right? Where we are very confident that this bounding box contains an object. So we find the valid indices, and if there are no valid indices, we return. But if there are valid indices, we basically copy the bounding box coordinates to prediction boxes. We copy the class labels to labels, and finally we copy the masks only for the valid labels to this masks, and this is what is returned. Okay, so we get the masks, we get the bounding boxes, and we get the class labels. Now we have to wrap this thing up, we have an instance segmentation API where we are going to pass in the image path and the threshold. So the very first thing we do is get the, call the get prediction method or function that we had just defined and get the predictions, right? We pass in the image, we pass in the threshold, we get the mask, bounding boxes, and the prediction classes which are above the threshold. Next, we read the image. This is using OpenCV, convert it to BGR format from RGB, convert it to RGB format from its original BGR format. And then we decide, there is some calculation we do to figure out what should be the thickness of the lines that we use to draw the rectangle. We figure out the thickness of the text, and this is based on the image size, etc. The calculations are simple. You could use a different one, but you can also use a fixed width, but we decided to do some based on the size of the image. Okay. Next, we go over all the masks, right, that are present for the image. We find the bounding box coordinates, right, the top left and the bottom right corner. We go and find the mask. Remember, this random color mask takes in a mask, it takes in a binary mask and returns a colored mask, right? Some random colored mask which we generate. And then we blend it with the original image. So you can imagine we had a mask, right? And this mask could be a sheep, right? And it is one sheep out of the 3, right? So this mask contains the outlines, or not just the outlines, but all the pixels that belong to one particular sheep. So we extract that class and create this RGB underscore mask. This is a colored image. So it is the same. It looks the same as this mask, but this is a binary mask. This looks black and white. This is a colored mask. And now we are combining the original image with the colored mask, and we are giving this colored mask a weight of 0.5. So it doesn't completely overwrite it. It basically adds a little tint to it, right? That is what this add weighted does. So if you look at the syntax of add weighted in OpenCV, this is the first image. This is the amount of weight for the first image. This is the second image. This is the amount of weight for the second image. And then this is an offset for us. The offset is 0. We are not going to put an offset there. And you get the final image. Okay. Next, we want to find a color for our bounding box. And we, this code is very similar to the one in the previous notebook. We essentially, for every class, we have randomly selected a color, and we are just going to assign that color based on the class, right? So based on this predicted class, we are finding the color. Then we draw a rectangle, which takes in an image, the 2 points, color, thickness, and then we draw the rectangle. To draw the label, so this part, let me just show you. So we have basically overlaid this image with this semi-transparent colored mask. Then we have created this bounding box, and now we are creating this box which contains, it has to be, we are first going to draw a solid box of this color, this pink color, and then we are going to write on top of it person with white color. Okay, so you can see here we first find the width and height of the rectangle of the bounding box of the text. Using that, we figure out whether we want to draw the if there is enough space, then we want to actually put this text on top of the bounding box. And if there was not enough space, then we would put this inside the bounding box. All right. So that is what this calculation is doing. So outside means we can safely place the box outside. And you can see here, based on whether we can place it outside or not, it is being placed outside, or otherwise the box is being placed inside. Then we draw a rectangle, and this is a colored rectangle, and it is completely filled up, right? And finally, we put text on the image, and then we use the predicted class, which is the person class, as you had seen in that example. And then we basically put the thing at the right place, right? So all these various things are basically based on the thickness, etc. we had calculated. Look up how to use put text if you are not familiar with the syntax, but all it does is puts the text person in that box that we had created. And finally, we show this image. All these information was being put on the image, right? And we loop over this and put it on the image. So that's it. Now we are ready to use this example. Again, the download file utility, it downloads a file from the internet. We have seen this before in other notebooks. I'm not going to go over it now. We create an inference directory, and we where all the information is stored. Next, we basically download this image which we have already uploaded for you, and we are going to use this, open this image and show this image, right? So we just downloaded this image. Now we have seen how to use this. We are going to transform this. We are going to create an image tensor, and we are going to do a prediction. All right, and then we look at what the prediction, the 0th element of that structure does. You can see we have boxes, we have labels, we have scores, and we have masks, right? And the bounding boxes, right? These are elements, 4 elements. You can see x1, x0, y0, and x1, y1, which is the top left, and the bottom right corner, and so on and so forth. Labels is basically what is the class that we have found. In this case, there is a person class. There is only a single person. And then we have scores, right? And you can actually, there are 2. You can see that there are actually 2 labels here. Both belong to the person class. But look at the threshold scores, right? The score for the first one is almost 1, and the score for the second one is 0.1. So when we do the thresholding, only this human is created. So it's possible that it is actually, so it detected this person, but it may have another bounding box which is similar, but somewhere else. So we don't know exactly where it is. It's actually at this location. We are going to ignore that bounding box. So if you it created 2 overlapping bounding boxes or something like that. So it think that there is a bounding box, there is a person somewhere here. Okay, so now we do the masking, right? We see where the mask, we threshold the mask, because the mask has values from 0 to 1. We threshold it. Anything above 0.5 is 1, and anything below 0.5 is 0. And that's why you see this nice binary mask. Okay. So you can, the reason this is still showing it has two channels. This mask has two channels because you can see that we had two objects detected. One of them is a fake object, and we are going to filter it out using this confidence score. Okay, so now we basically look at mask 1. We know that mask 0 is the right one. Mask 1, we are going to filter it out. Okay, so you can see that this is the mask that was created, and then we use random colors, right? That random color mask function, which basically colors this mask from white to this randomly colored mask. All right, and then we are going to blend. So this gets blended with the original image. So original image plus 0.5 times this image. Wherever it is black, it doesn't affect the image, but wherever you have a color, it half of this color gets added to the image. So you see this tinted image, and this is what it looks like. All right. So now let's go and download another picture and run the whole thing. Instead of going step by step, we'll run instance segmentation API on it. This is the original image, and we run this model on the image. You can see that it detected all the people, and it also created masks for every person. It is hard to see, but every person has a tinted mask on top of it. Similarly, we download images of these cars, and we run the model on it. Here, the threshold is 0.9. Previously, we had used a threshold of 0.75. Sometimes to get good results, you have to play with the threshold and choose which one it is. If you have a large data set, then you have to run some experiments on the large data set to see what kind of false positives and false negatives is acceptable for you. And based on that, you choose the threshold. Okay. Another example where we have, multiple instances. We have car, truck, and person. And this image you have seen before. You can see that we have colored all the cars differently, even though, they all belong to the car class. Examples of two birds. Again, example of a more complex scene where we have people, we have handbags, and we have traffic lights, etc. This is an example with a horse. And you can see here, sometimes the results may not be 100% accurate. So here you can see that, it detected more horses than there are, right? If you look at this, there are 4 horses or 5 horses, but it detected 6 horses, first of all, and the location is also not correct, right? So this is a more complex scene. In such examples, let's say you run into these examples where it's not doing a good job, you can fine tune with your own examples, right? Fine tuning and training, it's not covered in this course, but there's a mechanism to fix this. I just wanted to convey that even though this result doesn't look great because the horses, they are not segmented properly, these are the kinds of examples you need to find in your actual application, right? When you try to run this kind of pre-trained model on your own application, you will find several cases like this. Maybe 10% of the cases you may find that it's not giving the results that you want. In those cases, you can still use the pre-trained model and fine-tune it with your own data, and suddenly you will see that the results improve, right? So the mechanism, the training mechanism, and how to do these things, that's covered in our paid course, Deep Learning with Pytorch. And there are several other courses that make you an expert in deep learning and computer vision that are available at OpenCV University. You can go check them out, opencv.org/university. All right, so now under low light conditions, you can see that it does a reasonable job, but sometimes you can have a problem. It actually thinks that the screen is a TV, which is not very far off. It's about right. But all these cases, you have to analyze, what are the kinds of failures you're getting, right? And how to improve it. That depends on what kind of training you will do subsequent to your pre-trained model. So these pre-trained models are great to get a baseline idea, right? When you're building an application, you always start with these pre-trained models and see how much, what is the quality you can expect, right? And then you can improve the quality significantly by training using your own data, okay? Another thing to keep in mind here, another thing to look at is obviously the inference time, right? Whenever we do this kind of, build an application like that, it is very important to see how much time this application is taking. You can imagine that image classification takes the least amount of time, followed by object detection, followed by image segmentation. And this one is a combination of both, right? So it has to do more processing to come up with these instances. And therefore you will see that, these things take longer. Again, to do this inference comparison on the CPU and GPU, we load the model, we put it on in eval mode. We then have this function that does, that runs it on the CPU as well as the GPU and outputs the result. Here you can see that, we are loading the image and converting it into a tensor. We are assigning device, right? We are saying that if the device is available, if CUDA is available, use CUDA, otherwise use CPU, right? And it also depends on this argument. If GPU is available, then if GPU is set to true, then use the GPU, otherwise use the CPU. Okay. So next, you basically send the model to the device, you send the image to the device, and then you with torch.nograd set, you do the model inference, and then you see you find the time and subtract the start time from it. This is basically the time elapsed, right, between this step and this step. Okay, so this is how you do inference. And if you want to do inference, we can basically go and look at all the images in the inference directory, and then we go over a loop and find out what is the average time. In this run, you can see that the average time on the GPU was 150 milliseconds, roughly 149.72 milliseconds. But when we ran it on the CPU, this shoots up to almost 6.4 seconds. For one image, it takes 6.4 seconds on the CPU, right? That is why so many people need to use GPUs for these heavy applications, right? So let's look at some of the applications of this. We can blur the image. In a Zoom call, when you're looking at a Zoom call, you can go and blur the background, and instance segmentation or even semantic segmentation can be used for blurring. Here's an example. Basically, you basically take, you have the image path, you set the threshold, and you find the mask, right? Just like using get prediction. And then you find the person which has, we want to select one person and blur everything out. And that is what we are doing. So all the person IDs we select from this. We find all the people, keep those people in the foreground and remove everything or blur out everything in the background. Okay. So we get all the masks for the people, and then we sum it, right? And this gives us the person mask, right? All the masks, we have combined them, and we get the mask for the person. So here you can see that this is the image we got. There is a single person in it. And then we read that image, we create a blurred version of that image. So the entire image is blurred with a 21 by 21 Gaussian kernel. And if you don't understand this, it's basically, 21 by 21 tells you that this is This is a convolutional kernel of size 21 by 21, which is run over the entire image to blur the image. And if you don't understand this concept, right, what is a Gaussian blur? These are very fundamental things in computer vision. You need to know these things. And we do have a course called, we have a foundational course called Fundamentals of Computer Vision and Image Processing at OpenCV University, where we go over all these technical details, right? We start from the very basics and teach you all the various things that are necessary for becoming an AI engineer, right? It trains you for a career in AI. All these things are covered in those courses. So basically, we have an image, we have a blurred version of that image. We get the person mask, and then we basically the mask we get is a binary, is a single channel mask. We have to repeat. We have to create three copies of that mask so that we can create an RGB image. Now this person mask becomes, it looks the same. It's a grayscale image, but there are 3 channels in it. Okay, and the reason we did it is that we want to operate. We want to actually take these colored images and mask them out. So here we are creating a final image where if person mask is 1, then we use the original image. Otherwise, we use the blurred image, right? So, and then we get the final image and we display it. So this was the original image and this is a blurred image. You can pick some element of it. For example, you can look at this area, right? The leaves are completely blurred. You can see this area, the leaves are not blurred. And the person's face is sharp in both these examples. So that was our notebook on mask RCNN. In the final notebook, we will cover YOLO. YOLO is an object detector. It is a single shot object detector. So all these methods that we have covered so far, these are 2-shot, right? And we had explained when explaining RCNN, fast RCNN and faster RCNN, why the inference happens in 2 stages, right? And that is why these methods are called 2-stage methods. But YOLO is a single stage method, and initially it gave blazingly fast results, but the quality was compromised. But newer versions of YOLO, the current versions of YOLO, they are just fast and they also give very good results. All right. They give better results than faster RCNN. So nothing is compromised. You get a very fast object detector and it is also very high quality. All right. So we'll cover YOLO in our next notebook. Thank you.